Today's topic is isomerism, which is a property of monosaccharides. So, sugars exhibit various types of isomerisms. So, let us see what is isomerism. Compounds having same molecular formula but different spatial arrangement of atoms are known as isomers. So, now let us look at the different types of isomerism shown by monosaccharides. Monosaccharides have same molecular formula but differ in arrangement of atoms in space around the carbon atom. So the different types are the stereoisomerism, which is of two types, enantiomers and diastereoisomers, followed by functional isomers, which is again of two types, aldose and ketose, followed by optical isomerism, which is also of two types, that is the small d and small l isomerism. The fourth type is epimerism. The fifth type of isomerism shown by monosaccharides is anomerism, which is again of two types, that is alpha anomerism and beta anomerism. And the sixth type of anomerism shown by monosaccharides is pyranose and furanose forms of isomerism. So before we proceed to different types of isomerism in detail, let us try to understand few terminologies. So here we will take a look at what is asymmetric carbon and penultimate carbon atom or reference carbon atom. So we are taking glyceraldehyde as the reference molecule here. Asymmetric carbon atom has four different groups attached to it, and the carbon which has four different groups attached to it is known as the chiral center, and it becomes the reference molecule for that compound. Glyceraldehyde is also explaining to us what is penultimate carbon. So the second last carbon in monosaccharides is known as the penultimate carbon. In glyceraldehyde, this is carbon number 2. In glucose, the penultimate carbon is carbon number 5, and therefore carbon atom number 3, 4 and 5 are the reference carbon atoms in tetrose, pentose and hexoses respectively. Glyceraldehyde is the reference molecule for all monosaccharides, as all higher monosaccharides are formed from glyceraldehyde. Now we will discuss about stereoisomerism in detail, which is of two types, that is enantiomers, which form mirror images, and diastereoisomers, which do not form mirror images. All types of isomerisms have one thing in common, and that is their molecular formula is same. Stereoisomers are also known as D and L isomers. They have identical molecular formula but differ in spatial arrangement at penultimate carbon or the reference carbon. And this type of arrangement, molecules having this type of arrangement are known as enantiomers. So we will take example of glyceraldehyde and glucose here. In glyceraldehyde, you can see that in one molecule the hydroxy group is towards the right hand side in the reference carbon atom or the penultimate carbon. So when the hydroxy group is on the right hand side, it is known as D-glyceraldehyde, and when it is on the left hand side, it is known as L-glyceraldehyde. Similarly in case of glucose. So D-glucose has hydroxy group at the penultimate carbon on right hand side, whereas L-glucose has hydroxy group on the left hand side at penultimate or reference carbon. All these molecules show D and L isomerism. They are also enantiomers of each other. Naturally existing sugars in humans are all in D sugars. Let us take a look at what are diastereoisomers. Diastereoisomers are actually defined as non-mirror images, and they are non-identical stereoisomers. So they are a type of stereoisomers. Now example of hexoses is given here, in which there are more than one chiral centers, and the position of hydroxy group varies at more than one carbon. Because of this variation, they have different properties and therefore different names have been given to them. 8 such variations are possible for aldohexoses. Some examples commonly known are galactose, mannose, glucose, and glucose. Now, the enantiomers are capital D and L type of isomerism in which the variation is only at the penultimate carbon atom. The hydroxy group position is different only at the penultimate carbon and they are mirror images of each other. The number of isomers in a sugar molecule is equal to 2 raised to the power n. So the total number of isomers in monosaccharides possible can be found out by this formula. This is known as the Li-Bel-Wanhoff's rule, where n is the number of asymmetric carbon atom. For example, glyceraldehyde has one carbon asymmetric, and so there are two isomers possible. And for an aldohexose, the number of asymmetric carbon atom is 4, and so 16 different stereoisomers for aldohexoses exist. All carbohydrates except dihydroxyacetone have at least one asymmetric carbon that exists as stereoisomer. We'll now see functional isomerism, which is of two types, aldose and ketose isomerism. They have same molecular formula but functional group is different. So in case of hexoses, we will see here glucose, which has aldehyde group, and fructose, which has ketose group. So glucose is an aldose sugar and fructose is a ketose sugar. Both are interconvertible with the help of enzyme isomerase, and this is a very important reaction in the glycolytic pathway. The third type of isomerism is the D and L isomerism. Here the D and L are written in small alphabets and in italics, and it is different from the capital D and capital L stereoisomerism. Optical isomerismers have identical composition but they differ in direction of rotation of plane polarized light. So when plane polarized light is passed through it, the beam varies, and this is because of asymmetric carbon atom which causes optical activity. Let's see an example. When plane polarized light is passed here, there is clockwise rotation towards the right hand side. When the light is rotated clockwise to the right hand side, it's called dextrorotation, or it is shown by plus sign. That is why glucose many times is known as dextrose. So it exists as dextrorotation. Similarly, when the light rotates counterclockwise, it rotates to the left hand side, and this is known as levorotation, designated as small l or minus sign. D-fructose shows L type of optical isomerism. Therefore, stereoisomerism and optical isomerism are different. So you can see here that both glucose and fructose are D type of stereoisomerism showing different optical activity. Now we come to the epimerism, in which there is difference of hydroxy group position only at one carbon. They have same molecular formula but differ at single asymmetric carbon other than reference carbon. Here we will take example of glucose. Glucose has two epimers. One is galactose. In between glucose and galactose, the position of hydroxy and H ion are same except at carbon number 4. Similarly, glucose and mannose are also epimers, but the difference lies only at carbon number 2. In rest of the carbons, the position of hydroxy group and H ions are same in both glucose and mannose. So, glucose is convertible to galactose with the help of enzyme epimerase, and same way glucose can be converted to mannose by the enzyme epimerase. These reactions are important in our biochemical processes. We know that glucose has two epimers, that is galactose and mannose, but galactose and mannose themselves are not epimers of each other, but they are diastereoisomers, which means they vary. The position of hydroxy group and H atom vary in at more than one carbon atom. So now we can see the difference between enantiomers, diastereoisomers and epimers. The enantiomers form mirror images with regard to reference carbon atom, and here is the example of L-glucose and D-glucose. Diastereoisomers have more than one chiral centers, but they do not form mirror images, and example here is given of hexoses in which there are 4 different chiral centers, so there are 8 different diastereoisomers seen in aldohexoses. Epimers are two sugars that differ in configuration only at one chiral center other than the reference carbon atom. Glucose, galactose, or glucose and mannose are epimers of each other. Now we come to the fifth type, that is anomerism. This form of isomerism is due to cyclization, which creates an anomeric carbon, which is a type of isomerism. In this, the C1 carbon atom of aldose and C2 carbon of the ketose show anomeric carbons. This is because of asymmetry that is caused due to cyclization. It generates two types of configurations, that is the alpha and beta type of sugars. So here we are taking example of glucose. In this diagram you see that the hydroxy position is below the plane and therefore it is known as alpha D glucopyranose. Glycogen is synthesized from alpha D glucopyranose. The second diagram shows hydroxy group above the plane and therefore it is known as beta D glucopyranose, and cellulose is synthesized from it. The last type of isomerism seen in monosaccharides is the pyranose and furanose forms of isomerism. Many properties of sugars cannot be explained by the straight chain structures. So you can see that sugars are expressed as straight chain two-dimensional structures. This is known as Fisher's projection. And many properties of carbohydrates cannot be explained by this, and therefore it is seen the cyclic structure of monosaccharide, which is known as the Haworth projection. This cyclic structure, when it has 6 members in a ring, it is known as pyran, and when it has 5 members, it is known as furan. This is a property of pentoses and hexoses. They form hemiacetal rings, and this is due to reaction of an aldehyde group with the hydroxy group on the 4th or 5th carbon to form a furan or a pyran. So the alpha D glucose, which is shown in a Fisher projection, is cyclized to form either a pyran or a furan, which are hemiacetal rings. Thank you for watching. Like, comment and share, and subscribe to my channel.